Imagine a situation where a person taking their first step after a surgery. Now imagine a completely different situation. High above us, a huge telescope floating in space, steady enough to see the beginning of the universe. If I tell you what connects these two very different stories are a same kind of robot. It's difficult to imagine, right? Correct? Because whenever whenever we hear the word robotics, we think of something like a human-shaped robot or something like a four-legged machine, dog-like quadruped. But believe me, robotics is far more than that. Robots can be classified in many ways. They can be serial or parallel, rigid or flexible, mobile or fixed, and even a combination of this. A humanoid robot, which you know, a Mars or Moon rover, you would have probably seen, or a dog like quadruped, are all moving robots simply because they move on wheel or whether on legs. Similarly, they are all also rigid because they are made of metal structures, isn't it? But robots aren't always made of metal structures. There is huge world of soft robotics. Robots which are inspired by nature, which are designed to bend, mold, and move around like a living creature. Some move like octopus, while other worm and fish. So this is soft robotics. Each of these robot have their unique application and have their beauty of their own. But you know what? There's one kind of robot, and one of the robots which you would have probably seen. It's a serial robot on the factory floor, right? Where you see something like our arm, one link connected to another link, and at the end there is a gripper or the end effector. You can paint, you can lift some object with that. They are called serial robots, which move link by link by link. But what has been close to my heart ever since my PhD is something called as parallel robots. Now, as I told, serial robots move link by link by link. A parallel robot moves all its link all at once. It's like a synchronized dance. So the basic structure of a parallel robot is there is a fixed base, there is a moving platform as you can see, and there are multiple legs in between so that the alignment to the final platform can be given. Now, this is something called a Stewart platform, which is a 6 degree of freedom parallel manipulator. Now, it has a fixed base and 6 legs, something called as parallel Stewart platform. Yeah. So, when you talk about parallel robots, they are not simply, they are very steady, they are very precise because they are not moving link by link, they are moving all at once. Now, it's not just a robot in theory, or it's not a machine in the lab. It's far more than that. You won't believe, in hospitals, it is used for realigning the bone of some patient. Far in space, it's used in engineering marvel of NASA's James Webb telescope to see galaxies that are billion light years ago. You would be surprised to know that 18 Stewart platforms are used to precisely align the 18 hexagonal mirrors of the James Webb telescope. It's not limited to this. They are used to protect delicate optical instrument in space from vibrations. They are used in gaming, flight simulators, and much more. So parallel robots isn't just limited to the lab. Now you'll ask, how does a single robot does so many tasks? It has a magical power. Engineers call it, in layman term, engineers call it 6 degrees of freedom. So this robot can move, can glide forward and backward, then side by side, it can move up and down, then it can tilt both ways and twist that all this movement independently. And hence, it has so many applications. Now, let me bring you a bit closer to my PhD that I did at Indian Institute of Science, Bangalore. Have you ever tried taking a selfie and your hand shook a little? What happens? The image comes blurry, right? Agree? Because the tiniest of vibration makes the image unstable. Now let's scale up this problem to a bit technical. Imagine a camera or a spacecraft that is 500 kilometers in the orbit, and a vibration or a deviation as small as 1 microradian, which is equivalent to 0.0005 degrees, barely nothing at all, right? Can shift the image or can shift the line of sight on the ground by about 5 meters. So that's like you are trying to capture someone or your friend, but you end up taking an image of someone who is feet away from him or her. So that's how things are done. Now, my PhD was about using Stewart platform to do this micro vibration. As I told you about the magical 6 degrees of freedom, Stewart platform will sense the vibrations which are coming in 6 degrees of freedom and will cancel out. Now, all of you will ask where this micro vibration or vibrations are coming or this noise are coming in the spacecraft. It comes from various reciprocating and rotating components in the spacecraft. And they are crucial because they control the orientation of the satellites. So you cannot remove them. The only way is to isolate them. Now, forget these technicalities. If you want peace in your life, what strategies do you adopt? If you all start making noise and I want peace, I would prefer to isolate myself and move out of this auditorium. The other strategy would be, if someone out of you single person is making noise, I will ask him to go out. So you either isolate the source or you isolate the target. So same way, if you draw an analogy, there are two ways in engineering term. Either you mount the camera or the payload, whatever you want to isolate, on the Stewart platform, such that the vibration doesn't reach the payload from the disturbing sources. Or you keep the disturbing sources on the Stewart platform such that the vibration doesn't come to the spacecraft bus itself. Now that depends on how much quantity, whether the disturbing sources are there. So it depends on mission to mission, which strategies you are adopting. Now, while the basic idea, now this work we did with ISRO, Indian Space Research Organization, for their future mission. The basic idea till now may have sounded to you a bit simple, but it's not actually as simple as it sounds. The design is far more than that. And for me, I think PhD is not about building something, but finding new ways and innovative ways of doing something. So now coming to a bit technical again. As you know, I have talked about the magical 6 degrees of freedom. Each of these 6 degrees of freedom comes with their own challenge. The challenge is resonance peak. You would have heard of this term, resonance peak. Go back to your 11th class. Soldiers are not asked to march in sync when they are passing over the bridge. This is, even though bridge is so gigantic and soldier maybe some 5 or 10 or 100 in numbers, but still every system has its resonance frequency. And what happened at resonance, you can see the peak, instead of isolation or instead of the peak being reduced, the peak is amplified at the frequency. So when you march at sync in the bridge, and if your tapping frequency matches the frequency of the bridge will start shaking violently. Correct? Now you see a figure where I have marked spring and damper. In between, there is one ground and there is one block and there is camera which I have placed. Now you say that's simple, but I was talking about 1 degree of freedom. This becomes more challenging when 6 degrees of freedom come together, because if you are operating your camera at the region of isolation of the first mode, at this point, if you see, if my pointer is visible, but while you are able to say, I am able to control my movement in this direction, there is a resonance peak at that same frequency you can see of the other degree of freedom. So while I am controlling one degree of freedom, I am still dancing violently in the other degree of freedom. Now, keep this technicality aside. What is the problem? If I ask you, you all must have lived in hostel at least once in your life. Everyone wants a single room or a double room or a triple room, max to max. You will never prefer people will multiple, I mean 6 or 7 people. Why? Because everyone has a different sleep schedule, right? If there will be 6 people, you will never have quiet region or quiet time in your room because someone wakes up early, someone sleeps early. But for optical payload to operate in space or delicate instrument, you need that complete silence. So what is the ideal solution? I'll ask all these 6 students living in the hostel that you all should align your schedule so that you sleep together, you wake up together, so that at least at night you will have a complete silence. And that is what we have done. I have made sure that all the 6 resonance peaks are coming at one place so that all of them make noise together and leave rest of the spectrum quiet. So this is in technical terms called dynamically isotropic Stewart platform, where you are aligning all the 6 degrees of freedom so that in very layman term, it's like organizing chaos. You are organizing the noise at one point and then your dampers come into play. So when you have peaks at different places, the dampers can work in a particular frequency bandwidth. So where it will go and attack, you have to tell them which point it has to go to attack. But when you align it all at one place, all 6 degrees of freedom, your damper can attack at one go and then it reduce the peak. But again, resonance peak can be reduced, it cannot be avoided. But for extreme cases, we are operating in the region of isolation, but in extreme cases, we never know that it may get into resonance, so we need to reduce the peak. So we didn't stop at the theory. We went, did the software simulation, got the similar result, and then we went ahead with the prototype, which we designed for ISRO, as you can see in the figure. And we managed to get all 6 natural frequency at one point. This work was highlighted by the official page of Indian Institute of Science and recognized wide recognition. And after this work, lot of organizations approached us, including DRDO for defense application, to extend this work. But what really touched my heart was not from aerospace or defense background. It came from a medicine field. A doctor from NHS UK came with a proposal. Can we use this Stewart platform to gently align bones on Earth, basically your tibia bone on Earth? I mean, how beautiful. Using those magical 6 degrees of freedom, which is basically aligning your telescope to see galaxies, you are using the same concept to realign the bone. And that's where today's topic comes from, that is from healing step to cosmic leaps. Now, how this works actually? So, when a patient has a fracture, they wear a lightweight Stewart platform on their leg. So basically, if they have a fracture, they have 2 broken bone segment. One that is mounted on the top platform rigidly, and the other which is mounted on the bottom platform, as you can see in this figure. So what you have to do is carefully, as I told, this parallel manipulator all move in sync together. So you need to know how much daily, step by step, you need to move each of the leg such that they perfectly align. It may look simple, but it's a complicated solution because your legs may broke in different orientation. I mean, it can twist and all those things. So you cannot just join them in translation, but also rotate them by certain degrees. So all those have to be taken care simultaneously. So this is the problem. And what solution we did is doctor need not to do anything. We don't do it in India right now, but we are working to do it in India right now. So what doctor has to do is just upload the 2 views of fracture into our customized software. What we do in engineering, one front view and side view, right? Same way in medical, in orthopedics, we called it AP view and lateral view. The doctor just need to upload these two images into our customized software. And what this customized software has in the backend, it has the equation governing this Stewart platform. So the doctor, in few clicks, he just need to mark the bone axis, and from there software takes care of everything. Now the software will figure out how much your bone is out of place. And based on that, it will give a prescription to the patient. Now what this prescription contains is day by day how much each leg has to be moved. I mean, there are different colored legs, so how much you are going to move each day. And this movement cannot be very fast because our tissues cannot tolerate fast movement. So it has to be gentle and steady. Of the order, maybe 1 mm per day or 1 degree per day. So that constraint has to be respected. Moreover, if you see, after that, you can see bone are going to align. So what's the beauty of this thing? Now the patient have the prescription in their hand. They need not to stay in the hospital. Take the prescription, go back day by themselves or asking their family members to move each of the legs of the Stewart platform, and slowly, steady and steadily, day by day, the bones realign. And what is the advantage of this? Is it's non-invasive. It will lead to minimum because you are not doing an open fracture here. So day by day, what is going, better wound healing will be there and minimum blood loss will be there. So there are a lot of advantage, and it's not only limited to only say fractures. There are many orthopedic conditions in which it can be applicable, like lengthening of the leg. Many people have one short leg, one long leg, so it can be used there. There are many medical conditions. There also it can be used. So that is the application. Now, to be honest, everything till now I told was sort of garbage because, I mean, you may not be working on parallel robot, but what is very important, it's what you take away from this. There can be many aspects on which you can take away. The first is technological aspect. Because you all are engineers, what do you take away from this work? Because in this work, I have showed you a broad spectrum, right from aerospace application to medical application, right from your foot to space. What I want to convey you in terms of engineering, that basics of something or foundation of something, whatever you do in life, whether you are doing engineering, whether you are doing a photography or whatever, or you are an army, basics should not go away. If you have basics, you can apply something on ground, and if you have that basics, you can apply something in space. Now, more important takeaway is what you take in your life, and that is why I kept the title from healing steps to cosmic leap. So if we learn how to heal our steps after an accident, after a defeat, whether in robotics, whether in science, or whether in our life, we are unlocking the power of small steps. And those small steps are the ones that prepare us for the giant leaps, right? So that is why it is said, every small step that you are taking is preparing for your own cosmic leaps.